Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The planet Mercury. A fiery embrace. Mercury's intimate dance with the sun. In our solar system, bathed in the relentless glare of the sun, lies a world of extremes. Mercury. This small, rocky planet holds the title of closest neighbor to our star, forever locked in a celestial dance of fire and ice. Unlike the vibrant, swirling gas giants further out, Mercury presents a stark, cratered landscape, sculpted by the sun's immense gravitational pull and scorching radiation. Here, a single day stretches longer than a year on Earth, and the temperature swings are enough to melt lead by day and freeze carbon dioxide solid by night. Unveiling the mysteries of Mercury is a journey into a world unlike any other in our solar system. A rocky past. Unveiling Mercury's formation. Traveling back billions of years, we can piece together the story of Mercury's formation. Theorized to have formed alongside the rest of the solar system roughly 4.6 billion years ago, Mercury's early history might hold the key to understanding its unique characteristics. Current scientific understanding suggests that it likely began as a much larger protoplanet, a swirling mass of dust and gas coalescing around the young sun. However, a giant impact event, possibly a collision with another celestial body the size of Mars, is believed to have significantly altered Mercury's course. This violent encounter is thought to have stripped away much of the planet's outer layers, leaving behind the iron-rich core that dominates its composition today. The theory of a giant impact aligns with Mercury's high density, the densest planet in our solar system besides Earth. This suggests that a significant portion of the lighter rocky material that would have formed Mercury's mantle may have been ejected during the collision. The remaining core material, rich in iron and other heavy elements, then solidified to become the dominant feature of the planet. A portrait of a planet. The surface of Mercury. Gazing upon Mercury's surface is like stepping back in time to the early days of the solar system. Unlike Earth's ever-changing, dynamic surface, sculpted by plate tectonics and volcanic activity, Mercury presents a desolate landscape, a world seemingly frozen in time. Craters, the indelible scars of ancient impacts, dominate the Mercurian surface. Billions of years of relentless bombardment by asteroids and comets have left their mark, etching a story of violence and resilience on this scorched world. The lack of a global magnetic field on Mercury exposes its surface to the constant onslaught of charged particles from the sun, further eroding the surface features and contributing to the cratered terrain. However, Mercury's surface isn't entirely homogeneous. Vast, smooth plains called calorous basins, believed to be the result of ancient impacts that vaporized the surface rock, offer a glimpse into the planet's violent past. These colossal basins, hundreds of kilometers wide, are thought to have been formed by impacts so energetic that they excavated the planet's mantle, spewing molten rock across the surface. Additionally, long, winding cliffs known as scarps crisscross the landscape, formed by the planet's contraction as its core cooled and solidified. Studying these diverse surface features is crucial to understanding the geological history of Mercury and the processes that have shaped this enigmatic world. Beyond the craters and plains, volcanic features hint at a period of past volcanic activity on Mercury. Though not currently active, these features suggest that the planet's interior may once have been hot enough to generate molten rock that erupted onto the surface. Understanding the nature and extent of this past volcanism can offer insights into the thermal history of Mercury and the processes that shaped its internal structure. A day unlike any other. The peculiar rotation of Mercury. One of the most intriguing characteristics of Mercury is its unusual rotation. Unlike Earth, which spins on its axis roughly every 24 hours, Mercury takes a significantly longer time to complete a single rotation, a staggering 58 Earth days. This means a single day on Mercury is longer than its year, which is the time it takes to orbit the Sun, 88 Earth days. This peculiar rotation, known as a tidally locked rotation, is thought to be a consequence of the intense gravitational pull of the Sun. Over time, the Sun's gravity is believed to have slowed Mercury's rotation and synchronized it with its orbital period. This synchronization means that the same side of Mercury always faces the Sun, leading to the dramatic temperature differences we observe on the planet's surface. The sunlit side experiences scorching heat, while the permanently shadowed side remains in a state of perpetual deep freeze. A world of contrasts. Scorching days and frigid nights. The consequence of Mercury's tidally locked rotation and close proximity to the Sun is a world of extreme temperatures. The sunlit side of Mercury bears the brunt of the Sun's relentless radiation, reaching scorching temperatures exceeding 430 degrees Celsius (800 degrees Fahrenheit). At these temperatures, lead would melt and even zinc, a metal with a high melting point, would approach its liquid state. However, the story doesn't end there. The flip side of the coin is the permanent night on Mercury. Because the planet lacks a thick atmosphere to trap heat, the side facing away from the Sun plunges into frigid darkness. Temperatures on the night side can plummet to a bone-chilling -180 degrees Celsius (-290 degrees Fahrenheit), colder than the surface of Pluto, the farthest dwarf planet in our solar system. This vast temperature swing, exceeding 600 degrees Celsius (1100 degrees Fahrenheit), presents a significant challenge for any potential future missions to Mercury's surface. Landers or rovers would need to be specially designed to withstand both the scorching heat of the day and the extreme cold of the night. A thin atmosphere. A mercurial mystery. Earth's life-sustaining atmosphere is a protective shield, filtering harmful radiation and regulating temperatures. However, Mercury presents a stark contrast. It boasts a very tenuous and transient exosphere, a wispy envelope of atoms rather than a true atmosphere. This exosphere is primarily composed of sodium, potassium, and oxygen atoms, constantly being replenished by the solar wind, a stream of charged particles emanating from the Sun, and sputtered off by the Sun's intense radiation. The existence of this thin exosphere is a bit of a mystery. Gravity alone isn't strong enough to hold onto these lightweight atoms for extended periods. Scientists believe that the interaction between the solar wind and Mercury's surface plays a key role. Solar wind particles can knock atoms off the surface, creating a temporary population in the exosphere. Additionally, the decomposition of minerals on the surface by sunlight may contribute to the exosphere's composition. Studying the composition and dynamics of Mercury's exosphere can offer valuable insights into several aspects of the planet. It allows us to understand the processes that shaped Mercury's surface and the ongoing interaction between the planet and the solar wind. Furthermore, by comparing the exosphere's composition with the surface composition, scientists can gain clues about the types of materials present on Mercury. A search for water ice. Mercury's hidden treasures. Despite the scorching surface temperatures on Mercury, recent missions have hinted at the presence of a surprising guest: water ice. Radar observations by spacecraft like MESSENGER have detected reflective patches at the bottoms of permanently shadowed craters near Mercury's poles. These areas never receive direct sunlight, creating an environment where ice can potentially remain stable for billions of years. The presence of polar ice deposits would be a significant discovery, offering new insights into the history of water on Mercury. It's believed that water ice may have arrived on Mercury through various means, such as impacts by comets or asteroids containing ice. Understanding the extent and composition of these potential ice deposits is crucial to piecing together the puzzle of Mercury's volatile history and the possible presence of water in its past. A magnetic anomaly. The mystery of Mercury's faint field. Earth's protective magnetic field shields us from harmful radiation and auroras. In contrast, Mercury possesses a much weaker, localized magnetic field. This faint field is believed to be induced by the solar wind interacting with Mercury's exosphere. The solar wind, a stream of charged particles from the Sun, can interact with the tenuous atmosphere, causing some particles to become magnetized and generate a weak magnetic field around the planet. While weak, studying Mercury's magnetic field can offer valuable insights into the planet's internal structure and its interaction with the solar wind. The strength and direction of the magnetic field can provide clues about the properties of Mercury's core, such as the presence of a liquid outer core that can generate electrical currents. Furthermore, understanding the interaction between the solar wind and Mercury's magnetic field can shed light on the processes that shape Mercury's exosphere. A window to the early solar system. The legacy of Mercury. Mercury, often referred to as a fossil planet, serves as a time capsule, preserving a record of the early solar system's formation. Unlike Earth and other planets that have undergone significant geological changes, Mercury's surface features have remained relatively unaltered for billions of years. Studying the composition of Mercury's surface can provide valuable insights into the materials and conditions that existed during the solar system's infancy. The high iron content of Mercury suggests that the planet may have formed closer to the Sun than its current position. Over time, the gravitational influence of the giant planets like Jupiter may have caused Mercury to migrate outwards to its current orbit. Furthermore, by analyzing the types of minerals present on Mercury's surface, scientists can gain clues about the composition of the protoplanetary disk from which the solar system formed. a beacon for future exploration. Unveiling Mercury's secrets. Mercury, though the closest planet to Earth, remains a world shrouded in mystery. While missions like Mariner 10 and Messenger have provided invaluable data and images, much about Mercury remains unknown. The scorching heat, lack of atmosphere, and extreme temperature swings pose significant challenges for spacecraft design and operation on the surface. However, the potential rewards of further exploration are immense. Future missions, with advancements in heat-resistant materials and innovative landing technologies, could revolutionize our understanding of Mercury. These missions could involve deploying rovers to explore the composition of the surface, investigate the extent of polar ice deposits, and search for evidence of past volcanic activity. Unveiling the secrets of Mercury is not just about understanding a single planet. It's about piecing together the story of our solar system's formation and evolution. By studying Mercury, we gain a window into the processes that shape the building blocks of planets and the potential diversity of worlds that exist around other stars. As we continue to explore this enigmatic world, we unlock a chapter in the grand narrative of our cosmic origins.